We've already looked at some models for whole number multiplication. Now we're going to look at some algorithms for whole number multiplication, as well as algorithms and models for whole number division. So let's look at 36 times 52 and different ways that we could multiply those two numbers. And the first thing we'll look at is something called the partial product method. Now, if we were going to be multiplying 36 times 52, we would probably say we want to multiply the 2 in 52, times the 36. And that's exactly what we're going to do. But we're going to break it down a little bit more than that. We're going to say that the 2 in 52 can be multiplied times the 6 in the 36. And the 2 in the 52 can be multiplied times the 30 in the 36. The 5 in the 52 is really a 50. We can multiply that times the 6 in the 36. And the 5 in the 52, which is really a 50, will multiply the 3 in the 36, which is really a 30. So what we have is a list of products that we get when we multiply each of the digits, which represent a number because of its place in its place value. We multiply each of those digits times each of the other digits. And when we add together all of these partial products, we get our product of 1,872. Now there is a connection to algebra with this, and that has to do with something you probably remember as foiling when you have two binomials. So if we think of 36 as 30 plus 6, and we think of 52 as 50 plus 2, you can see that we have a binomial times a binomial. And you remember from algebra that if you multiplied the first terms, the outer terms, the inner terms, and the last terms, you could multiply those two binomials. This really is an extension of the distributive property. And once you add together all of those sums, you get the 1,872 that we got with our partial product method. It's exactly the same thing. We could use an area model to multiply these two numbers. The way we would do that is by representing each of the numbers as a length of a side of a rectangle. So 36 is 30 plus 6, and 52 is 50 plus 2. Then what we're going to look for is the area inside each of the rectangles that are inside the large rectangle. So for example, if we have a rectangle that measures 50 by 30, its area is 1,500. If we have a rectangle that measures 50 by 6, its area is 300. We have a rectangle that measures 2 by 30, its area is 60. And we have a rectangle that measures 2 by 6, and its area is 12. And if we add all of those areas together, we get the 1,872 that we got with the other methods too. The traditional algorithm is what you're probably used to. There really is place value going on inside this algorithm, because when we say 2 times 6 is 12, and we write down the 12 and carry the 1, what's really going on is we are saying 2 times 6 is 2 1s and 1 10. The 10 we are carrying so that we can combine it with other groups of 10. And then when we say 2 times 3 is 6, we're really saying 2 times 30 is 60. That's 6 tens plus 1. The 1 10 we carried is 7 tens. 7 tens is the 7 in 72. So you can see there really is place value going on here. But we probably have learned this algorithm almost like it's some sort of automatic machine-like thing that we're doing. There is place value going on. In fact, even in the next step, when we're going to multiply the 5 times the 36, 5 is not really 5. 5 is really 50. So when we say we're going to be multiplying 5 times 36 and we put that placeholder 0 in there, that is saying no, we're really multiplying 50 times 36. And 50 times 36 will give us a number that ends in 0. That's the same as what we'd get as we multiply 5 times 36. So now 5 times 6 is 30. It's really 50 times 6, remember. We're carrying the 3. And then 5 times 3 is 15, plus the 3 is 18. Remember, it's really 50 times 30 is 1500 plus the 300 that we carried, which is 1800. And so now when we add those two partial products, we get 1872, the same thing we got with the other methods. There's another way to multiply numbers, which is called the lattice multiplication method. It organizes the information according to place value, but it might not be real obvious how that's happening. So let's take the same problem. We already know what the product's going to be, and let's organize it according to this lattice method. So here's how the lattice method works. Since we have a 2-digit number times a 2-digit number, we're going to create a rectangle that contains 2 rows and 2 columns. We're going to put the digits of one of our numbers that we're multiplying across the top and the other factor that we're multiplying along the right side. And then we'll draw some diagonals that go from the upper left to the lower right. Now the place value is within the diagonals. So if you look kind of from the bottom right to the top left, that's where the places are. So now we're going to be multiplying these digits together. And for now, we can simply look at these numbers as a single digit times a single digit, but they really do represent numbers with a place value. For example, if we multiply 3 times 5, we get 15. Now that's not really 3 times 5. It's really 30 times 50, which is 1500. And if you look at where the 1 and the 5 are, the 1 is in the thousands place and the 5 is in the hundreds place. Remember, the places are along the diagonals. 6 times 5 is 30. Remember, that's really 6 times 50, which is 300. The 3 is in the hundreds diagonal, so we have the number 300. 3 times 2 is 6. Well, it's really 30 times 2 is 60, and look at where that 6 is. It's in the tens diagonal. And then 6 times 2 is 12. We know that 12 is 1 10 and 2 ones. The 1 is in the tens diagonal, and the 2 is in the ones diagonal. So now when we add along the diagonals, we're adding digits that are in the same place. So 2 is the only digit in the ones diagonal. 0 plus 1 plus 6 is 7, so we have 7 tens. 3 plus 5 plus 0 is 8. We have 8 hundreds. And then we only have 1,000. So there's our 1,872. Now since this is probably a new method to you, let's try it one more time. 93 times 83. We have a 2-digit number times a 2-digit number, so we'll make a rectangle that has 2 rows and 2 columns. We'll put one of our factors across the top, the other across the side, and draw the diagonals. Remember, the diagonals are separating the place values. Now if we multiply each single digit times each single digit, 9 times 8 is 72, 3 times 8 is 24, 9 times 3 is 27, and 3 times 3 is 9. Those digits are in diagonals that correspond to the place that the digit should be in according to their place value. So for example, when we multiply the 3 times the 8, we're really multiplying 3 times 80, which is 240. The 2 is in the hundreds diagonal and the 4 is in the tens diagonal. Now if we add along the diagonals, we're adding digits in the same place value. So 9 is the only digit in the ones diagonal. 4 plus 0 plus 7 is really 4 tens plus 0 tens plus 7 tens. That's 11 tens. So we have a ones digit of 1 and a tens digit of 10. Now remember, that's 10 tens, so that's really 100. That's why that's in the hundreds diagonal now. 1 plus 2 plus 2 plus 2 is 7. And we only have one digit in the thousands diagonal. So we end up with 7,719. What if we're multiplying numbers that aren't base 10 numbers? Well, we can use the same algorithms that we can use for base 10 in any number base. What we're going to find is that because it's easier for us to think in base 10, after all, we've grown up with base 10 brains, it might be good to think in base 10 as we multiply, but write in base 4. So if I'm going to use a traditional algorithm on this, I could say, well, 2 times 3 is 6. But 6 is a base 10 number. 6 in base 10 is 1, 2, base 4. So 2 is the ones digit, and the 1 is the grouped fours digit. Now I can say 2 times 2 is 4, plus the 1 is 5. That's a base 10 number though. That's equal to 1, 1, base 4. Now we're about to multiply the 3 in the 3, 2. It's in the fours place, so we're going to put a 0 in the ones place. And now multiply 3 times 3, which is 9. But in base 4, that's 2, 1. So we will write down the 1 that can't be grouped, and we will carry the 2 that can be grouped. And then 3 times 2 is 6, plus 2 is 8. But 8 in base 10 is 2, 0 in base 4. Now remember, when we write a number, it's a base 4 number. So when we add, we have to make sure that we're adding in base 4. So 2 plus 0 is 2. That's okay. 1 plus 1 is 2. That's a good base 4 number. 1 plus 0 is 1. That's also a good base 4 number. And then 2 is a good base 4 number. So the product is 2, 1, 2, 2, base 4. So what if we wanted to do that same problem using lattice multiplication? Could we do it? And the answer is yes. We could still set up our lattice the same way. We'd have to remember that these are base 4 numbers. So we can think in base 10, but we have to write in base 4. So when we multiply 2 times 3, we can think 6, but we have to write 1, 2. 3 times 3, we can think 9, but we have to write 2, 1. 2 times 2, we can think 4, but we have to write 1, 0. And 3 times 2 is 6, which we've already said is 1, 2. The diagonals still are telling us the place values for these digits. So if we add along the diagonals, we have 2 in the ones place, 1 plus 1 plus 0, which is 2 in the fours place. 2 plus 2 plus 1 is, well, that's 5. 5 base 10 is 1, 1 base 4. So there's the 1 we can't group, and the other one in the fours place that we did. And then 1 plus 1 is 2. So we get exactly the same product with the lattice multiplication as we did with a traditional algorithm. So let's try base 12. We'll go back to the traditional algorithm on this one. So 2 times t. 2 times t means 2 times 10. That's 20. That's a base 10 number. In base 12, that's a 12 and 8 ones. So 8 is ungrouped, 1 is grouped. 2 times 4 is 8, plus 1 is 9. Now 9 is a good base 12 number, so we'll write that down. We're about to multiply e, which is in the 12's place, so we'll put a 0 in the ones place. E times t, that's 11 times 10. 11 times 10 is 110 in base 10, but that's really 9 12s and 2 1s. So there's our 2 1s and our 9 12s. And then e times 4, let's see, that's 11 times 4 is 44, plus the 9 we carried is 53, but in base 12, that's 4 5. Now remember, when we add, we have to make sure that we're thinking in base 10, but adding are writing our final number in base 12. So 8 plus 0 is 8. That's a perfectly good base 12 number. 9 plus 2 is 11. In base 12, that's an E. Plus 5 plus, there's the 4. So 4, 5, E8 base 12 is our product. So let's switch gears a little bit and talk about whole number division. And we'll look at this division problem to give us some idea of what to call the parts of a division problem. The 6 here would be called the dividend, the 3 would be called the divisor, and the 2 would be called the quotient. There is a relationship between division and multiplication because they're inverse operations. So for example, if 6 divided by 3 equals 2, then we know that 6 equals 3 times 2. We can also look at some models for whole number division. One is called the set model or the partition model. So to partition something means to break it up into groups, and division really is a grouping process. So if we have 6 divided by 3 equals 2, then what we're saying is that we're starting with 6 objects, and we are dividing that into 3 equal sets. 6 divided by 3, 6 divided into 3 sets. So if we take 6 objects and divide them into 3 sets, we end up with 2 objects in each set, which is why 6 divided by 3 equals 2. Let's look at the set or the partition model again. What if we had 6 divided by 2 equals 3? What would that mean? Well, that would mean we have 6 objects, but now we're dividing into 2 equal sets. So if we take 6 objects and divided them into 2 equal sets, then the number in each set is 3. That's why our quotient is 3 this time. There's something called a missing factor model for whole number division. The missing factor model basically says that if 6 divided by 3 equals something we don't know, then 6 has to equal 3 times that thing we don't know. It's really highlighting the relationship between division and multiplication. So obviously the thing we don't know would have to be 2 because 3 times 2 equals 6. So the quotient would have to be a 2. There's a repeated subtraction model for division. Since division really is repeated subtraction, much like multiplication is repeated addition, we can demonstrate this division by using subtraction over and over again as long as we subtract the same thing. So if we say 6 divided by 3 is something, what we want to know is if we start with 6, how many times can we divide or subtract that 3 from the 6 in order to end up with 0. So we can subtract once, twice, to end up at 0. So since we can subtract twice, we know that 6 divided by 3 has to equal 2. There's another repeated subtraction model that involves subtracting things that are not the same. And here's how that would work. Let's say we want to find out what 678 divided by 6 is. Well, one way we could do that is by subtracting groups of 6 that are friendly groups of 6. So, for example, I can imagine what 100 sixes would be. 100 sixes would be 600. So if I subtract off 100 sixes, I'm left with 78. And now I want to subtract off another group of 6s that's friendly to work with, like maybe 10 more 6s. 10 more 6s would be 60. That would leave me with 18. Now remember, I'm trying to subtract off groups of 6. 18, I can see, has 3 6s in it, and that leaves me with 0. So now I just need to find out how many 6s did I subtract. So I subtracted 100 6s plus 10 more 6s plus 3 6s, 113 6s in all. So the quotient, when I take 678 and divide it by 6, would be 113. So how do we explain this idea of remainders when we do division? One way is by using a set model. So let's say we wanted to take 7 and divide it by 3. So remember, a set model, we started with a number of objects, in this case 7, and we're trying to divide this into 3 equal sets because we're dividing by 3. So if we do that, we end up with 3 equal sets that each contain 2, but there's this one object left over that we can't put inside any of the sets, otherwise the sets would be unbalanced. So the 2 objects in each set is our quotient, and the 1 object left over is our remainder. So that tells us that 7 divided by 3 is 2 with a remainder of 1. So let's look at dividing 137 by 4. And we'll use the traditional algorithm, and we'll just look at this like the way you were probably taught to do this problem. So you probably were taught something like this. Well, let's see, I can't divide 4 into 1. So I'll try to divide 4 into 13. Let's see, 4 goes into 13 3 times. 3 times 4 is 12. 13 minus 12 is 1. Bring down the 7. 4 goes into 17 4 times. 4 times 4 is 16 with a remainder of 1, so it's 34 remainder 1. And that's true, but we didn't really use any language in there that explained what was going on. So let's take a look at the National Library of Virtual Manipulatives and what you can see with using their base blocks to see what's really going on when we do division. So take a look at these blocks. This represents 137. We have one 100 block, 3 10 blocks, and 7 1 blocks. And if we're dividing this by 4, we want to break this up into 4 equal groups. Now if you look at the 100 block, there's only one of them. We certainly can't divide that into 4 equal groups. So we're going to take this 100 block and we're going to regroup it and make it equal 10 blocks. Now we're trying to divide this into 4 equal groups. So there's 1, 2, 3. We'll put the 4th one up here. And then we have 1, 2, 3, 4. So far so good. 1, 2, 3, 4. Okay, so I've got 4 groups that each contain 3. I've used up 12 of these groups of 10, but I have 1 left over. So I'm going to take that and regroup it by breaking it up into ones. And now I'll see if I can divide these up into 4 equal groups. So there's 1 group, 2 groups, 3 groups. That'll be our 4th group. So put 1 down there, 2, 3, 4. 1, 2, 3, 4, and 1, 2, 3, 4, and we've got 1 left over. That's our remainder. So how many are in each group? We've got 4 equal groups. We have 3 10s and 4 1s in each group, so that means we have 34 in each group with 1 left over. Now how does that compare to what happened when we did the division? When we did the division, we said we can't take 1 and divide it by 4. That was saying we can't take this 100 block and divide it into 4 groups that each have 100 blocks in them. So when we said how many times does 4 go into 13, we were now looking at that 100 block as being broken up into 10 blocks. We have 13 blocks that are the size of 10s. We were able to get 3 of those 10 blocks in each of the 4 groups, which meant we had used up 12 of those 10 blocks. that left us with one 10 block, which we then broke up into ones, and that gave us 17 ones. Those 17 ones we divided into 4 equal groups, and each of those 4 equal groups had 4 in them, which meant we had used up 16 of the blocks by grouping them, and that left us with one block left over. So you can see in the traditional algorithm there really is place value going on, but it sometimes gets a little bit obscured by the language we use when we describe the division. What if we've got base 4? Well, let's take a look at those base blocks and see how we would do this. So here's what that looks like with base 4 blocks. We have 3 blocks that are a size of 4 each, and then we have 2 ones. And we want to divide this by 2, so we want to divide it into 2 equal groups. So let's see, we could put that in one group and that in one group, but that means that we've got a block here that we can't divide into 2 equal groups unless we break it up into ones. So now we've got, well, you know what this looks like, 6 to me. It's actually in the base 4 world 1 1 or 1 2 because it was 1 4 and 2 1s, but now it's 6 1s. So we'll divide that into 2 equal groups. And we have how many in each group? Well, we've got 1 4 and 3 1s. So the quotient is 1 3. Now let's look at that with a set model. 3 2 base 4 divided by 2 base 4. So there's our 3 2 base 4. We're dividing it into 2 equal groups. We can certainly put one of those 4 blocks in each group, but then the other 4 block we can't divide into the other groups unless we split it up into 4 ones, and then we can put 3 of the ones in each group. So the number of blocks in each of the groups is 1 3. There's one that's a size of 4 and 3 ones. Now how do I do this with a traditional algorithm? Well, let's see. I could say I have 3 blocks that are a size of 4. If I want to divide those into 2 equal groups, I can put 1 in each group. That means I've used up 2 of those size blocks, which leaves me with 1 block that's that size of 4. I'd have to break that up and combine it with my 2 blocks that are a size of 1, which would give me, well, let's see. It would give me, I'm thinking in base 10, that would give me, that's my 6 blocks, right? Now I have to come up with a way to take that number of blocks and divide it into 2 equal groups. So multiplication may help me to see how many times I can get these blocks into 2 equal groups. And if I take 2 base 4 times 3 base 4, that gives me 1 2 base 4, which would mean I don't have any blocks left over. Last thing we're going to talk about is order of operations. Should be familiar to you. Order of operations says that if we have a lot of operations combining a lot of different terms or factors, there is an order that we have to follow to make sure that we have come up with a consistent answer. We have to simplify whatever's in parentheses first. We have to combine exponents next, multiplication and division from left to right after that, and addition and subtraction from left to right after that. So for example, if we want to simplify 15 plus 6 times 4 minus 10, we have to do the multiplication first. That takes precedence over the addition or subtraction. Then we have addition and subtraction, but we have to do those from left to right. So we do the addition first, and then we do the subtraction to finally have 29. So that's a look at multiplication and division of whole numbers in both base 10 and in other number bases.